Come to 22nd lectures on electrical machines, and remember that in our last lecture we were discussing about distributing a coil and derived an expression for distribution factor, and coils are distributed and the distribution factor will be generally less than 1, and we got this expression, that is K d. If I write the formula straight away, it was like this: sin m beta by 2 divided by m sin beta by 2. What is m? What is beta? Beta is the angle between two consecutive slots, angle between two consecutive slots. Okay, in electrical degree, and m is the number of coils which are distributed, Okay, so this is very important. Therefore, I will now first tell you how to what does this mean actually. It means that if you have slots here, okay, and if you have suppose 2 coils, these 2 coils each one of them is having 2 turns here, 2 turns you can easily see, and you could make them accommodate in one slots only, a pair of slots only, and then you connect these 2 coils in series here. Therefore, total number of turns will now become 4, as if it is a multi-turn coil with 4 turns. Now, rest of these slots are underutilized, nothing is there. Instead of doing this, what we are doing, the second coil we are suppose putting it here after 2 slot pitch. Then the coils are distributed in this fashion or by a 1 slot pitch like this. Now, in this case once again you connect them in series and get this 2 as your output terminals. These 2 should be joined and you get the output here. Now, if you do like this, imagine that your poles are moving here, the voltage induced in this coil will be lagging this coil if the field is moving, or if the field is stationary, that is what I was telling. If you move it from this to this voltage will lag this voltage. If you move it from left to right, if you reverse the direction of rotation, then this will be leading whatever is happening here, the same thing is going to happen after some time delay in this coil. That is why we were telling that the voltages induced in the distributed coils, they will be phase displaced in time essentially, and the resultant voltage will be sum of these 2. Naturally, this voltage when you distribute the coils, total voltage will be less than if all the turns were accommodated in a pair of slots, and the factor by which that voltage will be accommodated is called the distribution factor. So, what you do? You calculate the induced voltage for all the turns and multiply it simply with k d. Now, suppose in a simple example I am telling you, suppose you have a 4 pole machine, P is equal to 4. Okay. Total number of slot, this is slots, total slots is S, and that is say is equal to 24. Then how to calculate the slot angle beta? You can do it in several ways. One of the way is slots per pole, or 24 slots are there over 360 degree mechanical. Therefore, beta mechanical will be simply 360 by 24, and of course, I need beta electrical. This is electrical angle. So, it must be multiplied with P by 2, this mechanical angle divided by, multiply by P by 2. So, 4 by 2 into 360 by 24. This way it can be written, or you can see it is equal to 180 degree divided by 6, that is 30 degree electrical. This is the thing you have to put in this formula, and M is what? M is how many coils you are distributing. Instead of 2 coils, you could have 3 coils, although I do not have the third coil. Suppose this is displaced and this is present, and another third coil is there, it is kept here, and all these 3 are connected in series. That number is M. I will come. That is just for this thing I am telling. Suppose these are all. So, you distribute the coils by a definite number of slots. For example, by 1 slot I will distribute. So, beta electrical, this calculation is correct, 30 degree. Okay. Another way I calculate it is like this. See, slots per, always calculate the same result, slots per pole is 24 by 4, that is 6, and one pole pitch is 180 degree. One pole is equivalent to 180 degree electrical. So, beta in electrical degree will be 180 divided by how many slots make 180 degree. So, that by 6, 30 degree, that is the this thing. You can do it straight away mentally. I mean, total number of slots, slots per pole, you calculate, that is equivalent to 180 degree electrical, then divide by that slots per pole, that is 6, you get 30 degree. So, this is how you calculate, and then the induced voltage phasors in case of distributed coil. I will just tell you, review this. This is the resultant voltage for 2 coils, and if these 2 coils were not distributed, resultant voltage would have been this. Each one is E, here also E. But what this K D is telling you, that you calculate as if the coils were not distributed, whatever is the voltage, that you simply then multiply by K D if it is distributed to get the RMS voltage. That is the thing. So, RMS voltage of induced in a coil groups. So, these are called coil groups, one group, another. So, this makes these are the things. So, distributed coils you connect in series, then E can be written as root 2 pi that F, which comes equal to P n by 2, phi is the flux per pole, and suppose n is the total number of turns of both the coils, then that n into you simply multiply by k t. That is called the distribution factor. K d is distribution factor. And the reason for distributing a coil I told you and ask you to think about it. Okay. Now, there is another factor which is called pitch factor. Pitch factor, which is denoted by this symbol K p. P stands for pitch factor. Now, what is the pitch factor? Pitch factor is this. I told you for any coil like this, multiple turns are there. This is the coil terminal. So, when these are joined means it goes several times. So, these are the coils say 1 1 dashed. I told you try to make sure that if this is 1 0 I was calling, this is 1 dashed 0. I told you to see that the other coil side 1 dash 0 is, if 1 0 is under the center of a south pole at any time, try to see it is the 1 dash 0 is placed in such a slot that it comes under the center of north pole. That is opposite, under opposite polarity of equal strength it should come, so that you get maximize the voltage. Or in other words, the coil span, this is called span of the coil, and it is equal to 180 degree electrical. For example, in this machine the coil span should be, if you want to maximize voltage, slots per pole is 6, that is equivalent to 30 degree. If your first coil side in slot number 1, your return coil side should be in slot number 1 plus 6, 7. That should be the position of the coil. Okay. I mean, so in slot number 7 the return coil side must be present, such that this will be 6 slots, which is equivalent to 180 degree electrical, because 6 into 30 is 180. And this will ensure that the induced voltage is BLV, BLV, 2 BLV. These voltages will be additive in nature, or n into 2 LV, where n is the number of turns of this single coil. Anyway, so this is the idea. Now, the interesting thing is that okay, you can do it like this. So, suppose full pitched coil, you place it here, suppose the number of slots, it is full pitched. Now, what happens if suppose I shape the coil in such a way, it is not, this separation is not 180 degree, but suppose it is less by some angle, 1 slot pitch angle. Okay. Suppose it is placed here, that is the coil span is made, if it is 30 degree between the slots, it is made 150 degree. Then also I should get some RMS voltage across this, but this time it is expected the voltage will be less. Now, I will explain why it will be less and by what factor it will be less, and that factor is called the pitch factor. Had the coil been a full pitched coil, so such a coil which is having 180 degree electrical coil span is called in literature as full pitched coil. Instead of that, if you have a coil, so a full pitched coil, suppose it is, let us try to understand so clearly what I am telling. So, this is suppose a full pitched coil. What would have been a short pitch coil? So that this angle is 180 degree. You can also state this in terms of slot numbers, that is 6 as I told earlier for that particular problem. Anyway, I could have a coil which is, this is 180 degree electrical, it could be like this. You start here, go there, but come back from here. Although this diagram is slightly messy, it does not look very nice, but you get the idea. I could make a coil in this fashion. And this angle is not equal to 180 degree. In fact, it is less than with respect to, if this is 180 degree electrical, this is less by this angle, and this angle is, I will denote it by epsilon, and then this coil is called a, not a full pitched coil, a short pitched coil. And by what amount it is short pitched? It is short pitched, people say these words, it is short pitched by epsilon, degree it is short pitched. So, by what amount it falls short of 180 degree is the short pitched angle epsilon, and I am asked to find out what is the induced voltage between these two coils and compare it with this. So, this is 1 dashed, this is also 1, say this is another coil 2 dashed, having same turns, their starting slots are same, returning slots are different, and these two coils are moving in a stationary magnetic field. Then how to calculate the RMS voltage induced in these coils? Remember here, to calculate the RMS voltage, now I will go straight away to phasor diagram. This is, suppose this terminal is 1, okay, and this terminal I am telling O, because these two are joined, and this is 1 dashed. And suppose it is moving from right to left. Suppose the conductor, see, I will be often telling it is moving from left to right or right to left, but you must understand what is the difference between these two. Nothing great is difference, but the difference is, if somebody says it is moving in this way, the conductor is moving from left to right, I will say, oh, E 1 dash tau, this voltage is leading E 1 O, that is all. And if it moves in this way, field patterns remaining same, I will say then E 1 O will lead E 1 dash tau. Very simple, because 1 O first see whatever it sees, 1 dash tau sees after this much angle of 180 degree. So, in this case, suppose the coil is moving in this way with velocity v, fields are above and below, south, north, etc. So, suppose I say this is the E 1 O voltage. Where will be E 1 dash tau phasor? Sinusoidal voltage distribution, so that it will be sinusoidal only, time varying, we know that. So, E 1 dash will be then lagging it by 180 degree, whatever is happening to 1 O in terms of time, same thing is going to happen to 1 dash tau after 180 degree. So, E 1 dash tau will be here. And you recall we found out this E 1 0 I want to find out. What should I do? This point. So, I must find out the potential E 1 dash I want to find out 1 dash. It will be then be this phasor minus this phasor. So, E 1 0 will be E 1 0 minus E 1 dash tau, but E 1 dash O is here. So, I have to add to E 1 0 negative of E 1 dash tau, that is E 1 0 1 dash tau is here. To this you now add E negative of E 1 dash tau. The lengths are same, so that you will get twice the voltage. So, another way of telling that twice the voltage will be available if the coil sides are 180 degree electrical apart all the time. So, you will get twice E voltage. This will be the this phasor will be E bar 1 dash if it is moving like this. Similarly, you can do if it is moving like that, E 1 dash tau will lead E 1 0 and E 1 dash 1 will be the difference of these two, but in any case you will always get twice the voltage. Is that clear? Now, let us do the same thing for the second coil here. In the second coil, similarly, let us assume it is moving in this direction with some velocity, etc. So, and this point, or I will draw it much more cleanly, so that there is no problem in understanding. So, this is a short pitched coil, okay, red ones. This is 1 dashed and this point is O, and the span of the coil is not 180 degree, but it is 180 degree minus epsilon degree. This is the span of the coil. Therefore, what will be I would like to find out E 1 dashed is how much. Here also same thing. Suppose you assume the conductor is moving and your field above and below they are stationary. So, it will see south pole, north pole successively as it moves from right to left. So, suppose I say that E 10 is this voltage phasor. Assuming sinusoidal B distribution, this will be the phasor E 10. Now, the question is where is E 1 dash 0? It is not now, same thing is going to happen to this conductor 1 dash tau after 180 minus epsilon, not after 180 degree as in this case. So, E 1 dash 0 can be drawn like this, lagging this whole angle is 180, this angle is epsilon. This is the thing what is going to happen, is not. Therefore, I want to find out E 1 dash, which is nothing but E 10 dash 10 phasor minus E 1 dash 0. So, these two phasors, from this phasor I have to subtract this. How can I get that? So, this is E 10, to this you have to add negative of E 1 dash 0. So, add it parallel to this and so on. So, this is minus E dash, not E dash, E 1 dash 0, this phasor, and your resultant voltage will be this one will be your E 1 dash. Got the point? This is the thing. Therefore, voltage in each of the coil site, they will be, magnitudes will be same. If it is E, this will be also E, is not? Coil site voltage I am now sketching. So, what will be this length I want to find out. So, to find out that length, recall you drop a perpendicular from this point here, say A m, this point you call a geometry, and do not forget that this angle is epsilon, this angle too is epsilon, because these two lengths are equal. Therefore, the resultant voltage is this length, it will be epsilon, this is epsilon and this is oh sorry, one thing I made a mistake, this is epsilon, it does not ensure that this is epsilon, I mean it looks like it goes. So, I will redraw it here. So, what you do is this is E 10, then to this, and E dash 10 will be somewhere here of same length E dash 10, and this angle is of course epsilon, that is fine. Now, E 10 and these things you add. So, this is minus E dash 10 and I am telling this is your resultant voltage, okay. E 1 dash, okay, and this is the thing. Therefore, this angle will be how much? This angle is will be epsilon by 2 and this will be epsilon by 2. Why? Because this is epsilon, this angle is 180 minus epsilon, 180 minus epsilon, and this angle will be sum of these two external angle and these two sides are equal. So, everything is fine now. So, this is epsilon by 2 and this is epsilon by 2, and then you drop a perpendicular from this here A m, and your resultant voltage this length, say if I call it say some name, if you give say C d, length C d will be this plus this. So, magnitude of E 10 this into cosine epsilon by 2 and also another same thing E by 2. So, this will be 2 times this. This will be the voltage length C d. We will continue with this in the next lecture further, and I will take the ratio.